trying to balance our protons and neutrons in the form of our mass number and our atomic number. Okay? When we have a situation like this, we're just trying to balance our total mass. Okay? And that's what conservation of mass tells us. Now, it can get a little bit more complex than this, as you hopefully saw in your reading. Okay? Because let's say we have, once again, hydrogen coming together with oxygen to form water. And we know right now that if 4 grams reacts with 32 grams to form 36 grams of water, okay, what if this time I had 8 grams of hydrogen, 32 grams of oxygen, but I still only made 36 grams of water? What else am I missing? Yeah. Okay. Because we saw that 4 and 32 come together to make 36, but here, all right, I'm 4 grams off. Okay. And so that extra 4 grams is just 4 grams of hydrogen that's just left over. Okay. Because just because I have hydrogen and oxygen together doesn't mean they're going to come together to form water. All right. In this situation, once that oxygen's used up, I can't react anymore. So once all that oxygen's gone, that other hydrogen is just going to sit there. So now those of you guys who did the homework, all right, what does that mean oxygen is? We have a special term for oxygen in this case. It's limiting. Okay. Oxygen here is going to be our limiting reactant. We say it's limiting because once it's used up, all right, that limits what we can do here. So that means in this case, the hydrogen, we have an excess. So we have too much hydrogen, not enough oxygen. So that means we're going to be left with hydrogen in the end. Yeah. Well, now, we'll get more into detail in the next chapter, but for now, if we have something, does everyone have this? Okay. For now, if we have something like this, say we have carbon plus oxygen, and we'll say we start with 14 grams of carbon, 16 grams of oxygen, and that goes to make carbon monoxide, 28 grams of carbon monoxide, and 2 grams of carbon. Okay, so you should be able to judge from this which is our limiting reactant and which is our excess. Okay, so which one is that here? Which one is our limiting reactant? The oxygen again. Okay, and that must mean our carbon is our excess. So we can tell what our limiting reactant is just by what we have left over. Okay, so in this case, if we have carbon left over, we know that's our excess. That must mean that the other guy here, the oxygen in this case, is our limiting reactant. Okay? Good. Now, like I said, I'm going kind of quick so we can squeeze all this in. All right? But if you didn't do the homework, go back and look at it. All right? Read that chapter again. All right? So you can get caught up to speed. Okay? For conservation of mass means that we're not going to create or destroy anything. We're just going to rearrange it. Good. Now, let's go ahead and skip forward a little bit to that number 5. Okay, that was a little bit of trouble. Don't you do that? Okay. When you were reading about formula mass, all right, what was the book's definition for formula mass? Give me, what's an idea of what formula mass is? Can you tell me that in words? Okay. The sum of the atomic mass is the formula in the substance. Okay? On a simpler level, really the formula mass we can say is the molecular mass. So while if we look at the periodic table, we can really easily see the atomic mass is just written below each atom, right? Well, the molecular mass is found by just adding up the individual atomic mass for each part. So if I look at something like water, okay, what's the atomic mass of hydrogen? About 1. We have 2 of them. What's the atomic mass of oxygen? About 16. Okay. So that means that the formula mass or the molecular mass of water is just 18 atomic mass units. Now your book might just use a U instead of AMU, but both of them are telling the same thing. So the mass of water is 18 AMUs. What about carbon dioxide? What's the mass of carbon? 12. And then oxygen has a mass of 16 again. So the formula mass of CO2 is just 44 AMUs. That's it. Yeah. No. Remember, you'll always have the periodic table. Okay? So the only thing you need to know is that when we have a molecule, to figure out its molecular mass, just add up the individual pieces. Okay? No, that'd be a waste of time. I don't have that memorized. Okay? Yeah, and that's fine. Okay, you're going to see it both ways. I use AMU just so we can see what it stands for here as atomic mass unit. But when you have just U, it's the same thing. Okay? Good. Now, this brings us also to our next little law, next concept here. Okay? When I have water, or when I have carbon dioxide, I'm always going to have the same ratio here of hydrogen to oxygen. I'm always going to have this 2-to-1 ratio here for water. Okay? I'm always going to have this 1-to-2 ratio here for carbon dioxide. If I don't, I have a different atom. All right? What do we call that law? Anyone know who did the homework? What do we call that? You guys just don't want to talk to me today. I think I might actually be here. Nope. Okay? We call this the law of definite proportions. Okay? And so what this law of definite proportions tells us is that if we have something like water, okay, no matter if we just have one water molecule or a whole big tub of water, we're going to have 2 hydrogen atoms for every 1 oxygen. Okay? So if I have 1 water molecule, it's going to have 2 hydrogen atoms and 1 oxygen atom. If I have a glass of water here that has 10 billion hydrogen atoms, how many oxygen atoms is it going to have? 5 billion. Okay? That ratio of 2-to-1 is always going to be the same. If it's not the same, then we don't have water. Okay? On your homework, I think I added in something with that wasn't H2O, but was H2O2. Okay? Anyone here dye their hair blonde? Okay? See, now I'm surprised. You'll admit to that, but won't tell me the law of definite proportions. What did you use to dye your hair? What, bleach? What else could you use? Use hydrogen peroxide? Yeah. So that's what H2O2 is. That's hydrogen peroxide. Now, I could real easily drink a glass of water here right now, but would you want to drink a glass of hydrogen peroxide?
Not really.
Probably not. That'd probably be a good way to die real quick, okay? Or at least throw up and get sick for a few days, okay? And so just this one change, changing this ratio, changes that molecule altogether, all right? Water's always going to be 2 to 1. If it's not 2 to 1, it's not water, okay? Same thing with carbon dioxide, okay? We breathe carbon dioxide out every second, all right? Inhale oxygen, exhale carbon dioxide. But what if I take away this 2? What is this now? Carbon monoxide. Well, what's carbon monoxide? Yeah, that's why you have those carbon monoxides in your home, right? So you don't have because your heater can leak carbon monoxide and then kill you in your sleep. Okay?
That's always nice.
Well, yeah. So just this one little change, and we go from something that is around us all the time right now to something that can kill you real quick. Okay? Because this law of definite proportions tells us that we're always going to have this same ratio, no matter if we have one molecule or a whole bunch of those molecules. Okay? And well, it depends on the molecule. Okay? So water is always going to be 2 to 1. Carbon dioxide is always going to be 1 to 2. Let's say butane is always going to be 3 to 8. Okay? And so if you change this ratio, you change the molecule. Basically the same thing we saw before with our atoms. Okay, we know chlorine is always going to be chlorine if it has 17 protons. We can change the number of neutrons, we can change the number of electrons, but it's the number of protons that tells us that this is chlorine. Okay? This is water only if we have a 2 to 1 ratio. We can get different ratios of oxygen and hydrogen in the chemistry lab, but it's not water anymore. So it has to have this ratio to be water. Now, this also means that not only is this ratio 2 to 1, but the mass ratio is the same too. Okay? So the percent mass of hydrogen of water is always going to be the same. And that's what number 5 was asking for, and that's why it was a little bit more difficult. Okay? Because even though we have this 2 to 1 ratio here, okay, which of these atoms is heavier? Oxygen. Okay, if we look here, oxygen has a mass that's a lot bigger than hydrogen. So even though we have a 2 to 1 ratio here, that oxygen is going to take up a lot more mass than the hydrogen. And we can actually figure that out. Okay. So if we start with water, and we already said, what was our formula mass for water?
18.
Yeah. So our formula mass here is 18 atomic mass units. And now I want to figure out what percent of this is oxygen by mass. How do you think I'd go about doing that? Well, let's think about this in maybe a little weirder way. If I want to figure out what percent of my mass, all right, is, I don't know, my T-shirt, okay, how would I figure that out? I'd figure out what my entire mass was, I'd figure out what the mass of the T-shirt was, right, and then I'd divide them. Okay, well, I know it's kind of a weird example, but we do the same thing here, all right. I say, well, I need to figure out how many oxygen atoms I have in this molecule. Okay. Multiply that times the atomic mass of oxygen. Divide that by my total, which in this case is my formula mass. And then finally, multiply by 100%. Because we want a percentage. So in this case, in water, I have one oxygen atom with a mass of 16 AMUs divided by a formula mass of 18. And if I multiply that by 100%, what does that come out to be?
88.9%.
Yeah. So about 89% oxygen. Not water, but that was number 5, yeah. And I know, since only half of us turned in the homework, I'll be lenient when grading it. Okay, and I know, I hope, if nothing else, you realize that reading the book and doing the homework is a lot more difficult than hopefully having me explain it. Okay, I hope you at least see that little bit of value of me talking up here. Okay, but so we have 89% of this is oxygen because oxygen is so much more massive. All right. Well, how do you think I'd figure out what percentage hydrogen is? Well, yeah, it's the rest of it. Okay, I can say real easily that I know my total is going to be 100%, right? So I know that the rest of it should be hydrogen. But it's always a good idea to check yourself on the quiz or test. So I can just go back here and do the same thing for hydrogen and just say, well, in this case, I have 2 hydrogen atoms, each with a mass of 1. The formula mass is 18. Okay. I have to multiply by 100%. And so what's 2 divided by 18? Yeah, about 11%. All right. So it's a little bit of math, but still not that bad. Okay. Why don't we try something a little bit more difficult? I'll help you guys get this started, and then we'll move on. What about lead chromate? PbCr04. Why don't you guys take a minute, see if you can figure out what's the formula mass for lead chromate. That's a Pb there. Oh, it kind of looks like a 6. Use the periodic table. See if you can figure out what is the formula mass for lead chromate. It's the 15th, too. What do you guys get for this? Yeah, 322, 323, depending on how you round. All right, but basically we have 207 plus 52 plus 4 times 16. Okay, so we'll say 323. Okay. Okay. Well, let's say on a quiz or a test I asked you, what's the percent that's lead, what's the percent that's chromium, and what percent is oxygen? Yeah. I know, my handwriting's kind of bad. Okay. Okay. What's going to be the same here in all these before you get started? Okay. The 323 is going to be the same, right? Because that's not going to change. Not 326. That's not going to change. Good God, why do I keep wanting to write 6? Okay. What else is going to be the same? The 100%. Okay, we're always going to multiply by 100% because we want this in a percentage. Okay. We'll see if you can plug in the rest of that for me and figure out what percentage each of those are. Okay. What do you put up top here? Yeah, that's 207. What about here? 52. Yeah, so that 4 times 16. So what do you get for lead? 64%. What do you get for chromium? 16. And finally, what do you get for oxygen? Yeah, we'll round that up to 20. All right. How do you know right away that you're probably on the right track here? Because the numbers add up to 100%. No matter what we're doing, all right, all these percentages better add up to 100%. I mean, 99, maybe we did some too much rounding, okay? But 100%, that's what these need to add up to, okay? So we're saying here with lead chromate, there's always going to be a 1 to 1 to 4 ratio. And that means that lead chromate's always going to have 64% lead, 16% chromium, and finally 20%, which is going to be oxygen. All right? Good. Well, let's try to pull all this together then. Okay. Let's say we have another reaction. We have nitrogen plus oxygen. Ooh, if I can get that to right. Goes to make nitrogen dioxide. Okay. And let's say that you start with 14 grams of nitrogen, 34 grams of oxygen, and end with just making this hard on myself. Can't do math in my head. 46 grams of nitrogen dioxide. It's more difficult than it should have been. Okay. What's the chemical formula for nitrogen dioxide first? Not N2O, NO2, right? Because we learned that already, that when we don't have anything up front here, that just means we have 1. The dioxide means we have NO2. Okay? So what's the chemical formula for nitrogen dioxide? Or what's the formula mass? Yeah, so it's going to be 14 plus 16 plus 16, which is 46. Okay. What am I missing in this reaction here? How do you know it's 2 oxygen, 2 grams of oxygen?
Because you only have 2 oxygens and 16, so it's 32.
Okay. There you go. So if I start with 14 grams of nitrogen here, it's going to require 32 grams of oxygen. So I'm going to be left over with 2 grams of oxygen. So what is my limiting reactant here? Yeah. So my limiting reactant here is nitrogen because I have oxygen in excess. Good.
So is a ratio thing where you can pretty much just swap out A and B for grams?
Well, yeah. No, that's because I was doing this on the fly in my head right now. But at the same time, all right, we could have had, I don't know, we could have had 28 grams of nitrogen and let's say 70 grams of oxygen. Okay, so the ratio is still going to be the same. Okay. But now, how much nitrogen dioxide would I have made in this situation? I would have made 92 grams of nitrogen dioxide. And what would I have had left over? Would be, yeah. Okay, because I'd have, not 4 grams, because I'd have 32, so 64. So I'd have 6 grams. Yeah. Okay. So remember, limiting reactants, whatever is going to be used up. Okay, excess is whatever you're going to have left over. Okay, and we can figure out what this is by our formula mass. We good on that? All right. Let's start new material then that we didn't have on this homework. Okay, we're going to use this, but now we need to talk about, well, how do these molecules form to begin with? Okay, and so to start here, we need to go back to looking at the periodic table. Okay, if I look at the periodic table here, I look at oxygen. How many valence electrons does oxygen have? How many valence electrons? 6, right? Because it's in group 6A. So everything in group 6A has 6 valence electrons. Well, the thing we haven't talked about yet is why oxygen isn't happy with 6 valence electrons. Okay? Okay? Yeah, because it wants 8. And this all comes back to the Octet Rule. Okay? Now, once again, your book might have a slightly different definition of this, because I like to personify atoms a little bit. Okay? But the Octet Rule simply means that every atom wants a complete outer shell. Or outer orbit. Okay? That's what every atom is striving for. It wants to have its outer orbit full to capacity of electrons. So if I look at the periodic table right now, what is the only group that already has that? The noble gases, group 8A here. Okay? All these elements, all these atoms have a complete orbit. All right? That means they don't want to react anymore. This is also why all these are stable. All right? Where do we use these? Where do you use helium? Balloons. What about neon? Light. All right. Same with argon. Okay? If I took a lighter to a balloon filled with helium, what would happen? Well, it would pop, right? But it wouldn't really explode, right? It would probably, the resulting air would probably blow out the lighter. Okay? But what if I filled that same balloon with hydrogen, and I took a lighter to that. It would really explode, right? Because hydrogen doesn't have a complete orbit, so it wants to react, all right? And if I put a flame to it, it's going to react really violently. This is the same reason, all right? What are blimps filled with? Helium. Okay. Anyone see a video of the Hindenburg crash? Oh, well, okay. We can take a break from that then. Man, see, maybe I am getting older than I thought. YouTube. Seriously, raise your hand, how many people have actually seen the video of the Hindenburg crash? All right, so half of us, that's not bad. And nothing's going to happen, all right, because it's so stable, all right? Nothing's going to happen to any of these things here. You use neon and argon in these lights where there's this really high voltage because it's not going to explode, all right? Nothing like that's going to happen. Well, okay, because you can put a high voltage on there and get to emit light rather than explode, okay, which is what would happen with all these other guys. All right, and that's the same way even if we look over here at sodium. Sodium's a metal, okay? Do you know what would happen if I brought a chunk of sodium here and set it on the table? It would catch fire and explode just from the humidity in the air. This is just a metal, all right? We just leave it out there, okay? Depending on the humidity, this is Louisiana, so probably 5 minutes, okay? No. And this is why when you actually see people work with pure sodium, they do it under oil, so it doesn't react like that, all right? But everything over here wants to get to this group A, okay? And there are a couple ways this can happen, all right? And the first way is with an ionic bond, all right? An ionic bond is just when one atom gives electrons to another. That's it, okay? And so to understand these ionic bonds a little bit, we can talk about this Lewis dot system for representing atoms. Because remember, it's not the whole atom that's reacting. Even in that fire with that hydrogen in the Zeppelin, okay, it was just the electrons that were reacting. We don't care about that other stuff, okay? We only care about the electrons, and really we only care about the valence electrons. And so that's what this Lewis dot diagram is going to do, all right? We're just going to represent the valence electrons. So if I look at hydrogen, how many valence electrons does hydrogen have? 1, okay? 1. So 1 dot. 1 dot for 1 valence electron. What about helium? 2. 2 valence electrons, 2 dots. Go back down here to lithium. How many valence electrons? 1. Beryllium? 2. You guys see a pattern? So we just put dots around here for how many valence electrons we have. Okay? And because I don't feel like writing all these, I'm just going to use this picture from your book. Okay? So for every valence electron, we put a dot. So that means everything in group 1A here has 1 dot. Everything in group 2A has 2 dots. 3A, 3 dots, 4A, 4 dots, and so on and so on. Okay? Now, all of these atoms want to have a complete outer orbit. So if we look at something like sodium, for example, we see sodium right here is in group 1A, so sodium has 1 dot. Okay? So if we look at sodium, sodium has 2 options. Every atom has 2 options. Okay? Sodium could either gain 1, 2, 3, 4, 5, 6, 7 electrons and be kind of like argon, or sodium could lose 1 electron, making that inner orbit its outer and be like neon. What do you think is easier, sodium to gain 7 or lose 1? For it to lose 1, okay? I know this doesn't happen a lot in this class, but sometimes common sense and chemistry match up, right? It's a lot easier for sodium to lose 1 than gain 7. What if we look at the other end of the spectrum? With chlorine. Chlorine's in group 7A, so it has 7 valence electrons. Once again, chlorine could either gain 1 electron or lose 7. What do you think's easier? Gain 1. Okay? So really, if we look here, what do you think is going to happen if I mix a big pot of sodium and chlorine together? I'm going to get salt, but what's going to happen to this electron in sodium? It's just going to, sodium doesn't want that electron, so it's going to give it to chlorine that does. Yeah. Well, this is why we eat table salt, right? But if you were to eat a chunk of pure sodium, okay, you die real quick, okay? I'm just saying, I mean, that the water would react with the sodium in your stomach and explode from the inside out. That's, yeah. You guys are the only section that made me think of that, so thanks for being the morbid section, I guess. Okay? But we eat table salt all the time. And besides maybe giving us heart problems in our 60s, all right, eat a bunch of salt's really not going to hurt us too bad. All right? So let's try something different. Okay? Let's try magnesium and oxygen. How many dots do I put around magnesium? 2. 2 valence electrons, 2 dots. How many dots do I put around oxygen? 6. Okay? 3, 4, 5, 6. What do you think is going to happen here? There we go. So magnesium is going to lose its 2 electrons, and oxygen is going to take them. Okay? Okay. Now, before this happened, how many total electrons did magnesium have? 12. How many total protons does magnesium have? 12. So what was the total charge on magnesium before this reaction? Yeah, neutral. Those protons and electrons balanced out. Well, what about now? Did this reaction do anything with the protons? No. But now we have only 10 electrons, right? So what's our charge now? Positive 2, right? Now I know that's kind of weird. We're losing electrons, but we're losing negative electrons, so we're becoming positive. If we look at the same thing at oxygen. Oxygen started with 8 protons, 8 electrons, so no charge. Now we have 8 protons, but 10 electrons. So now we have negative 2. Okay? So now magnesium is positive 2, oxygen is negative 2. Okay? So what's holding these 2 together, do you think? Yeah, it's that ionic bond, okay? But really, there's no physical connection between these 2, all right? They're not like, I don't know, holding hands, or there's not like, something tying them together. The only thing keeping them together are those opposite charges. That's it. Just those same electric charges we saw before are what's keeping magnesium and oxygen together. Okay? We call these things ions. Okay? And an ion is just simply an atom with a different number of electrons. Hence, ionic bond. Because remember, before we already saw about isotopes, right? So, let's look here at fluorine, I guess. Fluorine is always fluorine as long as it has 9 protons. All right? But it could have 10 neutrons, 11 neutrons, 7 neutrons, 6 neutrons, whatever. It'd still be fluorine, just a different isotope. In the same way, all right, fluorine, all right, with 8 electrons, or with 10 electrons, or 11 electrons, is still fluorine, it's just a different ion. Okay? So ions like this just have a different number of electrons. And once again, these ions can have vastly different properties, all right, from their starting atom. Because if I go back here and look at Salt. What charge would I have on sodium here if I lost one electron? Yeah, just positive one. What about chlorine? Negative one. Okay, we already talked about sodium, all right? Sodium's going to catch fire and explode when it explodes to any water. Does anyone watch MacGyver? Yeah. Remember, there's actually, okay, you guys should do this for homework. Go find the MacGyver. He actually uses a piece of sodium to blow open the door and escape. Now, Mythbusters proved that was not possible, but still, all right, sodium's cool. You need a lot of sodium, that's true. Okay. Same time, chlorine. What do you use chlorine for? Yeah, but, okay. I was thinking more like common uses, but ever go into like a pool and smell that pool smell? That's actually chlorine. Okay. You pour chlorine into a pool to kill bacteria and other stuff there. At the same time, all right, what happens if there's too much chlorine in that pool? It burns. All right, you open up your eyes underwater, all right, it burns, and if there's too much chlorine, it can actually bleach your hair, okay? So chlorine in its pure state, not that good, all right? But ionic chlorine, we eat that all the time. That's, yes, you're definitely right about that. Because really chlorine is a main component in bleach as well. All right. So yeah. So the difference between this ion and pure chlorine is big. Okay. Let's try a couple more of these. Not stock system. Let's say I have lithium and sulfur. How many dots do I put around lithium? 1. Okay. How many dots do I put around sulfur? 6. Well, no spoiling the fun. Okay. Well, right away we can see that lithium only has 1, so it probably wants to lose that 1. Sulfur has 6, so it probably wants to gain a couple. But if lithium just gives its 1 to sulfur, lithium's happy now, but sulfur's still not. So you're absolutely right. I do need another lithium atom here to make sulfur happy with its 8 electrons. So when I mix lithium and sulfur together, I'm always going to have 2 lithiums for every 1 sulfur. Okay. Because what charge would you expect on lithium? Yeah. You have a positive charge on each of these. And what charge would you have on sulfur? -2. Yeah. So this is a good time to take a break and summarize all this. Okay, why don't you guys help me with this? Ionic bonds. Tell me one thing we know so far about ionic bonds. Make atoms happy. Well, you can put that on the test, you know, but that's the way I like to think about it. I know it's a little juvenile, all right, but I think of an atom, all right, such as sodium. It's not happy in its pure state. That's why it's so reactive. That's why it's going to catch fire and explode, because it wants to be bonded with something else to have that complete orbit. Okay, so that's what we mean when we say make atoms happy. All right, we want them to be stable. Okay, so how is that going to happen here? Okay, we're going to have a transfer of electrons. We're going to have this transfer of electrons from one to the other. Okay, what else do you notice about the atoms we've talked about so far? If we go back and look at these, and we're not done after this, by the way, we still have plenty of time. Well, no, because you always have to have something gain and something lose. But in this one, we have lithium and sulfur. Here we have magnesium and oxygen. Here we have sodium and chlorine. it's always a metal and a non-metal. Okay? Ionic bonds only form between metals and non-metals. Okay? What happened to all those metals? If we looked at sodium, no, they reacted, okay, but sodium has one valence electron. What happened to that one valence electron? It lost it. Magnesium has two valence electrons. What happened to those electrons? Lost it. All right. What about lithium? Okay. So really, all of these metals lost electrons. Okay. And if these metals lost electrons, what did that mean? Okay, non-metals gain. And so when we lose electrons, we become positive, and when we gain electrons, we become negative. Okay? Good. You can write down a test. As long as you know what that means when you say make atoms happy.
What does it mean again?
It means that we want the atom to have a complete orbit. All right? The atoms are not stable in the sense that they're very reactive if they don't have that complete orbit. Okay? Pure chlorine by itself is going to, it kills that bacteria and stuff in the pool because it reacts with them. Okay? Why don't you guys try, I want you to try one of these for me. Okay? Using this dot system, and only the dot system, tell me what happens when you have magnesium and nitrogen come together. See if you can make it so that each atom has a complete orbit. If I mix a big bucket of magnesium and nitrogen together. Yeah. Because like we saw before with lithium oxide, you might need more than one of each atom. Well, no, for now, you just do whatever you have to do. No, we don't have to model what these atoms will actually look like yet. Or ever, probably in this class. But let's go through this. All right, you guys tell me what you did. What did you start with? How many dots are on magnesium? 2. What about nitrogen? 5. Okay. So what's the first thing you did here? Yeah, all right. We gave the 2 magnesium to nitrogen. We're still missing 1. So what do we have to do now? Add another nitrogen, or probably need to start with another magnesium. Okay. So what's going to happen now? Yeah. So 1's going to go over here. So now nitrogen's happy. Yeah. So I need another nitrogen. Okay. Need 1 more magnesium. Yeah. So now we can say, all right, what charge would each of these magnesium atoms have? Yeah, 2, right? What about the nitrogens? -3. Okay. So if I have magnesium and nitrogen mixed together, I need 3 magnesium atoms for every 2 nitrogen atoms. Okay. Now, can everyone agree that was possible to do that, right? But if I come look around at all your papers, all right, it's going to look like a mess, isn't it? Right? Okay. Well, luckily, there's a shortcut. All right. There's an easier way to do this. Okay. Because if I look here, each of these magnesium atoms had a +2. So the total positive charge was 6. Each of these nitrogen atoms had -3. So the total charge here was -6. So really, in the end, this molecule doesn't have any charge at all. Okay. We can use that to help us out. Because if we go back and look at this periodic table, if I can find it, all these in group 1, all right, 1 valence electron. What's most likely to happen to that 1 valence electron? Lose it, all right? And so what charge would it have if it lost it? +1, right? What about group 2? If I have 2 valence electrons and I lose 2 of them, +2. What about group 3? +3. What if I skip ahead here to group 7? -1, right? Because everything in group 7 just needs to gain 1, so it'll be a -1. What about group 6? -2. Group 5? Okay. Ooh, what about group 4? Well, what have we already said? Metals are going to lose electrons, become positive. Non-metals are going to gain electrons, become negative. So what do you think is going to happen to carbon and silicon here? Lose. Yeah. And these guys down here? Yeah. That's it. So just by looking at this, we don't have to memorize anything besides the fact that everything in group 7 is going to be -1. Everything in group 6 is going to be -2. Well, yeah, I could be tricky and ask that. That's what? Oh, that just, don't worry about that. This actually goes in right here. So it'd be at the end of that. So what this means is we can actually use the charge to determine what our atom is going to be. So if I even go back and look at something kind of simpler, at, let's say, potassium and oxygen. Okay, what charge would you expect on potassium? -1? +1, right? Okay. What charge would you expect on? Yeah, -2. So how many potassium atoms do you need to balance out 2? Okay. Because if I have 2 positive and 2 negative, I'm balanced out. Okay. Now if I do the same thing with the dots, all right, potassium has 1 dot, oxygen has 6 dots. So potassium's going to give up one electron to oxygen. This potassium is going to give up its other electron. So we still have 2 potassiums for every 1 oxygen. Okay. So either method is going to give us the same answer. Okay. Why don't you try a couple more of these before we talk about our last subject? Okay. Why don't we start with calcium and chlorine? Okay. Strontium and nitrogen. Okay. Rubidium and carbon. And finally, my most difficult one, indium and silicon. Use whichever method you like, all right, but see if you can figure out what those ratios should be. All right. What charge did you expect on calcium here? +2 and -1. So what ratio do you have here? CaCl2. Okay. What about strontium? What charge? And nitrogen? So what ratio do you need here? 3:2. What about rubidium and carbon? What charge do you expect on rubidium? Carbon? So 4:1. And finally, indium silicide. Yeah, so +3 -4, 4, 3. There we go. And so once again, this is why we don't need to say how many we have when we say the names. Okay? Strontium, I spell strontium, nitride is always going to have 3 strontium atoms for every 2 nitrogen atoms. Okay? Rubidium carbide is always going to have a 4:1 ratio. Calcium chloride is always going to be 1:2. Okay? Because it can't be any other way. If you look here, there's also a little trick. All right? See if we have the 2+ and the 3-.
It's just opposite.
Yeah, if we just flip these, we get our right numbers. Okay? Same with down here, 4, 1, okay, 4, 3, 2, 1. Now the only time you have to be kind of careful about this is if you have something like calcium oxide. Okay, what charge would you expect on calcium? +2. What about oxygen? -2, right? So if you flip these here, you get 2 and a 2. Okay? But really it's a 1-to-1 ratio. So you just have to be careful to get the lowest number you can. Okay? Now, the very last thing I want to talk about before being done for today, I promise, okay, is what to do about those guys in the middle. Okay? What do we call these? Transition metals. Okay? They're metals, so what does that mean? They're going to lose electrons. Okay? But we can't just look at the group number and say how many they're going to lose. Okay? We actually have to say what it is. So for example, iron 3 is going to have a +3 charge. Gold 2 is going to have a +2 charge. So this stock system here uses Roman numerals to tell us what the charge is going to be. And that's it. So instead of having to even look at the group number, we just say, what is the Roman numeral here? The only bad part about this is we have to know a few Roman numerals. Okay? How's everyone's Roman numerals? Count to 50? No. Really, the only ones we need to know is we only need to go to 4. Okay, what's 4? IV, yeah. Okay, because you're never really going to have a charge greater than 4. Okay, so if we can go to 4, we'll be good. But other than that, they behave just like they would in any other system. Okay, so if I have iron 2 chloride, what charge do you expect on iron 2? +2. What about chlorine? -1. So iron 2 chloride would be what? FeCl2. Yeah, FeCl2. Okay? In the same way, you can put this in when you write it out too. So if I have silver 1 carbide, what's the chemical formula for silver 1 carbide going to be? Ag. Ag, we have to keep that 1 in there, but Ag4C. Because each of these is going to have a +1, each of these is going to have a -4. Because it's carbon, so it's in group 4, and it's a non-metal, so that means it's going to be a -4. Okay. So if you haven't done that homework, go back and look at it again, because it's going to help you for the quiz and test. Remember, we have a test next week. We'll still have a quiz this Wednesday. Okay. So you should be able to do through 14 here. All right? I'll see you guys on Wednesday. Oh, I don't have a stapler. That's fine, though.
Okay.
Sign-in sheet, too? Oh. Thanks.